So if you've got a single battery of voltage E, if you hook that up to a single resistor, we'll call it of resistance R1. I mean, finding the current's pretty freaking easy here. You got current coming out of here. It goes straight through a single resistor. You can just use Ohm's law, and the reason is Ohm's law says the current through a single resistor, let's say current through R1, is going to be equal to the voltage across that resistor. Now, I know the voltage across this resistor is the entire voltage of the battery because there's only one resistor in this circuit. Or if you like, you can do the loop rule if you really want to be careful. You rise up E, so that's plus E, you drop a certain amount. So when I loop rule, I add up all the changes in voltage. I add up all the voltages around a closed loop. You set it equal to 0. So when you go through the battery, that's plus E. When you go through this resistor, minus whatever the current through that resistor was, times the resistance of that resistance, because Ohm's law says that that's IR is going to be the voltage across a resistor. And there are only two things. So if I move this to the other side and solve for I1, I'm just going to get E over R1, which is really easy. That's how much current flows through this single resistor. Okay, so that's easy. What if instead you had two resistors in series? These are called series, R1, R2. Some of you probably already know the rule for figuring out how to, write this as one equivalent resistance. So there's a trick. There's a trick to reducing multiple resistors to a single resistor. So maybe you're like, oh, that's too easy. Check out this one here. If we look at this problem, this is 2019 AP Physics C. This is the second part. There's resistors all over the place. So you can't just say, oh, Ohm's law for this 200 is going to be the voltage of the battery over 200, because that's not necessarily the voltage across that resistor. So when you have complicated circuit diagrams with multiple resistors, you typically have to reduce them to a single resistor, and there's really just two ways we do that. Resistors in series or in parallel. And you figure out what equivalent resistance there would be and replace that section with a single resistor, and you simplify, simplify, simplify until you get to this case here where there's one resistor and one battery, which we know how to do. Okay, so the next simplest case besides one resistor is two resistors. These are called series because it's one right after the other. The thing that's really true here, the way you tell if two resistors are in series, is that the current that flowed into one resistor all flows right into the next resistor without getting distracted on a different path or anything. There's no junction in between them. So if all the current through one of these resistors equals all the current through the other, you know they're in series. So that's important because when you have a complicated diagram, you might be like, wait, I don't know if these two are in series, but you could just check. If one resistor right after the other, so the current that flows through the 100 all goes through the 50. There was nowhere else for it to go, so the 100 and the 50 are in series. So if you have two resistors in series, the rule is pretty easy. You can write the equivalent resistance as just R1 plus R2. Now maybe you've just heard this rule. Let's just derive it really quick because it's really easy. All we're going to do is the same thing we did on that previous single resistor problem. We'll start over here. We're going to loop rule. Loop rule is always how you derive this stuff. So when in doubt, loop rule. If you just knew nothing except the loop rule, you can get pretty far. So what are we going to get? You add up all the voltages around that closed loop. The first thing you went is from the battery from negative to positive. So that's a plus epsilon because you went from negative to positive. You increased in electric potential. And now you're going to drop. Anytime you go with current through a resistor, you're dropping. So minus the I, and there's only one I here. Like there's no junctions in the circuit. So there's a single I. The I that flows into R1 equals the I that comes out of R1. You don't lose any charge. Charge is conserved. So don't make the mistake of thinking that you lose current as it flows through a resistor. That's not true. The current loses electric potential energy as it flows through, but you're not destroying any charge here. Charge is conserved. So the current that flows into R1 equals the current that flows out of R1. The thing that changes is that the electric potential energy of the current on one side of the resistor is bigger than on the other side of the resistor. Okay, so you have I times, well, you went through two resistors this time, so we're going to have a drop across R1, so I times R1, and then another drop across R2, I times R2, then you get back to the beginning, that all equals 0. So if we just solve this, look what we get. We get epsilon equals, I'll move these I's to the other side, and you can just factor out a common factor of I. You get I times R1 plus R2, the quantity, because these are the same I. So you just factor them out. You solve for I here, and you get the I that's going to flow in this circuit, or at least the I that comes out of the battery, is going to be epsilon over R1 plus R2. So just compare that to what we got previously. I here was epsilon over R1. So if you wanted to know, all right, how much current comes out of the battery, it's as if. So finding the current that comes out of this battery is what we're really doing. It's as if you've replaced these two resistors with one single resistance. This is just Ohm's law. Ohm's law says that I equals epsilon over R. So if you replace this whole circuit here, you just get rid of this. So one resistor, what we're saying is that if you replace that with one resistor with a resistance of R1 plus R2, the battery would not know the difference. The exact same current would be coming out of the battery, because look at our formula here. This battery doesn't know the difference between two resistors of R1 and R2 or a single resistor of R1 plus R2. So this is why you can replace two resistors in series with a single equivalent resistor that just adds up to the two resistances of both of them. Now, like, there is a difference. It's a different circuit. You have one resistor instead of two resistors, but what we mean by equivalent is that the battery is none the wiser. You replaced these resistors, and the battery's like, yeah, it looks good to me. I feel the exact same resistance. I'm pumping out the exact same current. And so this is the formula, and that's how you get it. That's how you derive this formula for the equivalent resistance of series resistors. So that's not too bad. How would you derive it for parallel resistors? Let's say you have two resistors in parallel, so R1 and R2. So now how do you figure out how much current this battery would pump out? In other words, how do I replace these two single resistors with one single resistor? So let's do the same rule. We're just going to loop rule. When in doubt, loop rule. We'll come over here. We'll just take this path first, and we get epsilon plus, because we went from negative to positive. So we add an epsilon, we go through resistor in the direction of the current. So this time, current flows out of the battery, and then some goes this way, and some goes the other way. So you got current splitting off now. So you had the total current that came out of the battery, comes over here, and now there's a junction. So the current that came out of the battery is going to split off two ways. It won't be necessarily equal in both directions. If these resistors have different resistance, it's going to split off in a different amount. Whichever resistor has more resistance will get less current. That's counterintuitive, but it makes sense. More resistance gets less current. A lot of people think, oh, bigger resistor, better resistor, more current. But bigger resistor, more resistance, less current. So whichever one of these has more resistance gets less current. So we follow this loop. It's not too bad. I've got epsilon for the battery. I come through R1. There's only one resistor here. You're like, oh, shoot, this is pretty nice. Minus, so whatever this I is here, I got to give it a name. We'll call this I1 because it's current through I1. So I come through there, and I got I1 times R1. That's it, equals 0. And so you're like, well, shoot, that just means that I1 equals the voltage of the battery over R1. And so not too bad. That just looks exactly like it did for a single resistor. And so you might be like, well, that's weird. Let's do another loop. Come over to here. We'll go through this path right here. And again, we only went through one resistor. We didn't go through R1 this time. So we're going to get plus epsilon of the battery minus, I got to name this one. We'll call this one I2. So minus I2 times R2, and then that equals 0. And so we get I2 is epsilon of the battery over R2. And so you might be like, well, shoot, this just seems too easy. I mean, it is easy. So like, if this was the circuit you had, you wouldn't really need to even reduce these. You could just do a single loop. You got one resistor. The problem comes in when you have, like, you know, you got stuff in parallel, you got stuff in series. You really got to like reduce stuff for this problem. But if you really did just have this, then there would be no real need to reduce it. I'm just trying to do this so I can derive the formula so I can show you what it is. So if we wanted to write a formula for how much current the battery is going to spit out here, so we get the current that the battery is going to spit out is going to be voltage of the battery over, if I were to replace this entire section with a single resistance, what would it be? Well, just check this out. I know the current that comes out of the battery has to add up to I1 plus I2. So I've got I1 plus I2, and that has to be true due to the junction rule or conservation of charge. Whatever current comes into this junction, whatever current comes in has to equal all the current that comes out. So the loop rule just says that, you can't create or destroy charge here. Whatever current comes in has to flow out in some way. So I1 plus I2 would better equal I. And I'm just going to write this. So up here I'm going to say I is equal to epsilon over, I'm just going to write R equivalent. So let's just imagine we reduce this to a single resistor. In that case, the current that flows out of the battery would just be the voltage of the battery over that single resistance. Now I want to solve for this. So I'm like postulating, let's suppose you can rewrite this as a single resistor, in which case the current that comes out of the battery would be voltage of the battery over that single resistance. Well, now I got formulas for all these, so I can sub in here. So I'm writing as voltage of the battery over whatever my equivalent resistance would be. Like, I don't know what this form this would take, but I'm just saying it's some value, and I'm going to try to solve for it, equals I1, which I do know. I1 is epsilon of the battery over R1. And I2, which I also know, is epsilon of the battery divided by R2. And you're like, well, shoot, I got epsilons up top here all over the place. I can divide through by epsilon, gets rid of all of these, and you get your familiar, hopefully it's familiar, you get 1 over R equivalent for parallel resistors equals 1 over R1 plus 1 over R2, which is just the formula for reducing two parallel resistors to a single resistance. And just be careful, you have to like flip one extra time here. So if you really wanted to write what R equivalent is, it is 1 over R1 plus 1 over R2, and then 1 over that. Some people like simplifying this. They're like, hey, can't I just like cross multiply? It's like, yeah, you can. You could do R2 plus R1 over R1 times R2, and then you have to do -1 to that. So if I cross multiply, so you can kind of shortcut this thing if you want to. You could do R1 times R2 over R1 plus R2. And I guess a few things to note. This value for R equivalent for parallel resistors is always going to be less. The equivalent resistance for parallel resistors will always be less than either of the individual resistances. This is counterintuitive. Adding a resistor in parallel will always reduce the total resistance of this section. I mean, one way to think about it is like there's more lanes for the traffic now. Even though you've added a traffic jam, these resistances are kind of like traffic jams in the circuit. Even though you added a traffic jam, well, there's a new lane. Whenever there's more lanes in the highway here, that's a win, even if it's only a little bit of a win. Adding resistors in parallel increases the current that flows out of the battery because it reduces the resistance of this section here. So this is weird, but it reduces it. And if you had 4 in a row, all in parallel, and these are all in parallel, you really can just do 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. As many as you have in parallel that are actually all in parallel, you can keep going here. And this would be how you'd find the equivalent resistance. In other words, you can get rid of all of this mess, get rid of all of that, and you could replace it with a single equivalent resistor that has this value here, or whatever value you solve for R equivalent. Replace it with one resistance, and it's equivalent in the sense that the current that comes out of the battery is exactly the same as it would be in the case where you had those parallel resistors to the case where you replace all of those with a single resistance. So it's not the same circuit. Like there's no junction anymore. You don't have individual resistors. It's not going to be doing the exact same thing over here, but for the battery, it cranks out the exact same current. The battery is none the wiser, in other words, if you replaced that section of parallel resistors with one resistor that has this equivalent value. Whew. Okay, so let's actually apply this real quick. Let's actually try this out. So this is the second problem in this 2019 AP Physics C problem. It says the two 6-volt batteries are replaced with a single battery with a voltage E and a resistance of that as shown above. The voltmeter shows that the voltage across the 200 ohm resistor is 4.4 volts. So there was a previous part here. There were 6-volt batteries before. Now there's a single unknown voltage battery. They are telling us the voltage across the 200. They're just measuring it with a voltmeter. They're saying that that's 4.4 volts. And we want to find the current through the 50 ohm resistor. Okay, so that's the current over here. That's the one I drew right here. So I'll just call this I guess, shoot, I don't know. We're going to have to name these things. I'm going to call this I1. Sure. So that's I1 through there. We want to solve for that. One thing I could do is start reducing these resistors. So I find two that I know are either series or parallel. And you can't pick any two. This 150 and this 200 are neither parallel nor series right now. So let me make sure you know the rule here. The rule for parallel is, I'll just draw it on here. The rule for parallel is current has to come in, current has to split up, go through one resistor each before it does anything else, and then come back out. So if you had some branch over here, something weird like that, or you had another resistor in here, something crazy, you wouldn't be able to say that these two are in parallel. Parallel means the total current that comes in splits up two ways, goes through one resistor each, and then comes back together before anything else happens. That's the only way you could say these are in parallel. So we come up to here, we find two that are either parallel or series. These each ones are this 150. So the current that flows through the 100 is the same current that flows through the 50, therefore those are in series. So I can replace this entire section right here, this entire pink section right here. I can replace this whole section with a single 150 ohm resistor. And so I could redraw this if I wanted to. I could say that I've really got this battery, I'm going to redraw it over here, this battery with a 150 ohm resistor. I've still got this 200 ohm resistor, and then I'm going to replace this entire right section with a single 150 ohm resistor. And so I've got 200, 150, and 150. Now, the thing they told me is that the voltage across the 200 ohm is 4.4 volts. And that's useful because look at, if the voltage across this 200 ohm, if delta V across 200 ohm is 4.4 volts, the voltage across the 150 has to be 4.4 volts. If you don't believe me, just imagine doing a loop rule here. Just imagine loop ruling from there to there. You only have two elements. So whatever gain there had to be in one had to be lost in the other. These would have to add up to zero. These voltages across each of these would have to add up to zero. So whatever the voltage is across one has to equal the voltage across the other. And you might be like, wait, but one's positive, negative. That's just because I'm running backward through one of them. By backward, I mean against the current. And I'm running with the current. So you'd have like plus IR, minus IR. So plus whatever that voltage is, minus whatever that voltage is. And that'd have to add up to zero. So the two have to have the same voltage. Resistors in parallel always have to have the same voltage because of that, because you can run one single loop. And so the voltage across this 150 has to be 4.4. Now I could do Ohm's Law. I can just say that the current through the 150, I'll color code this. I used blue for that. The current through the 150 has to just be 4.4 volts over the resistance of 150, which is 0.029 amps. So that's the current that would flow through this section here, but what that means is that's the current that's going to be flowing through the 100 and the current that flows through the 50. This whole section is equivalent to this section, and resistors in series have the same current. So the answer to B, what is the current through the 50 ohm resistor? That's 0.029 amps. Now the next part says calculate the voltage of the battery. They didn't tell us the voltage of the battery, but we can figure it out. Now I've got a 150 ohm and a 200 ohm in parallel. So I can reduce these. I can say that this entire section from here to there is equivalent to, we can just use our rule. Remember, you could do the 1 over 1 plus 1 over the other equals 1 over equivalent. I'm going to do the shortcut. Why not? I'm going to do 200 times 150 over 200 plus 150. And if you multiply that all out, you're going to get 85.7 ohms. So you can replace this entire section with one 85.7 ohm resistor. So you'd have a battery, you'd have a single 150, and now you'd have one single, so this is 150, and then you'd have a single 85.7 ohm resistor. And now these two are in series. So you can just add up 150 plus 85. What's that going to be? You're going to have a single resistor here that is going to be 235.7 ohms. And so now we need to know what the current is through the battery. What was the current through the battery? Well, I shouldn't use this color. That was the current through the 150. The current through the battery, we'll just check it over here. Whatever current came this way, split up two ways. So you had a certain amount of current through the 200 and a certain amount of current through the 150 section. We figured out I1 was 0.029. We can figure out what the current is through the 200. So we know the voltage across the 200. We'll call this I2. So I2 is just going to be the voltage across the 200, which was 4.4. We're going to divide by 200, and that means the current through the 200 is going to be 0.022 amps. So I've got I2, I've got I1. Now I know what current flows through the battery. This current had to split up two ways. So the current through the battery has to be 0.022 plus this 0.029. So these two, I1 plus I2, has got to equal the current that came out of the battery. So this current that comes out of the battery is 0.022 plus 0.029 is going to be 0.051. Well, now I can figure out the voltage of the battery. So I can use Ohm's law for this equivalent circuit. Remember, by equivalent resistance, we always mean resistance you can replace a section of resistors with and have the battery be none the wiser. So the Ohm's law for this simpler circuit here is just going to be I is voltage of the battery divided by this single resistance. So 235.7. And I know this current here, this was 0.051 amps. So if I multiply that by this 235.7 ohm resistance, I get 12.0 volts is the voltage of this battery. And I found it by reducing all these resistors to an equivalent resistance, which was this entire section here. So this entire section from this point here to that point there, all of this mess over here can get replaced with a single resistor of 235.7, and the battery would be none the wiser. In other words, it cranks out whatever current it would have cranked out, and that allowed me to figure out how much current flowed through this battery or how much voltage this battery had. So recapping, if you've got resistors in series, you can replace those two resistors with a single equivalent resistance. You sum up the two. If you have resistors in parallel, well, you've got to either do 1 over 1 plus 1 over the other plus however many you got that are actually in series equals 1 over R equivalent, or you can reduce the whole thing and you get this little shortcut move here.